Okay, so welcome everyone. Today I'll be taking another TAship class of the course Solar Photovoltaics. And last week I could not take the class for not being well. So today I made an assignment which has some questions of the assignment that been provided to and some questions made by me. So today there are 10 questions based on the week 6 and 7 classes. So we can wait 5-10 minutes. In the meantime, I'll be showing you certain characteristics that has been taught in the week 6 and 7 classes, and then we'll see the assignment. So we'll wait for 10 minutes for others to join. In the meantime, I can give a quick recap. The quick recap is as follows that in the week 6 and 7 classes, sir has talked about the different solar cell device parameters, the IV curve, how do we calculate this VOC and eta efficiency. I have already made you people solve certain numericals in the last class, and then there is this circuit representation. Yeah, just a minute. Then there is this circuit representation where we have talked about the series and the shunt resistance, and then resistance and series and all, and the variations, etc., etc., the band gap effect, and all the limitations that are there in the solar cells. Then sir talked about the introduction to PV technologies, how does it bother, and other things like what should be the optimum values of different parameters. So I hope these things you have people gone through, and I have made this assignment today on the basis of these classes. So before going to the assignment, I would like to discuss some of the very basic things, and keep following this website if you really want to learn something related to solar cell. I'm myself learning in the solar cell field. I've recently started working. This website is a rambar for you. So first of all, let me talk about certain basic principles for the design of solar cells. You have to keep these things into mind. If you want to design a single junction solar cell, these are the principles which can maximize the cell efficiency. What are these? Increasing the amount of light collected by the cell that is turned into carriers. That means the absorbance of light. We have to design a material which should absorb more and more light so that we can get more and more carriers. How do we increase the collection? Increasing the collection separation of light generated carriers via PN junction. There should be a PN junction which where there is a separation, sufficient separation for increasing the collection so that they don't recombine very fast, minimizing the forward bias dark current and extracting the current from the cell without resistive losses. If you want to design a new material, for these are the basic principles that you have to keep into your mind. Except that, now what are the possible losses? After 10 minutes we'll definitely start assignment. I'm just giving you a quick recap by the time others are joining. There are certain losses. The major loss is the optical loss. What happens in the optical loss, as we can see, if there is a shading by the top contact coverage, this is a surface reflection that is happening, and this is a reflection from the rear surface. We have to minimize it. So how do we reduce it? Top contact coverage of the cell surface can be minimized by series resistances, anti-reflection coating, texturing, and other things, which is already been talked by sir in the class. Now how do we do the anti-reflection coating? This is the concept of anti-reflection coating. What we do, if there is a destructive interference which is occurring, then there is no reflected wave. If there is a constructive interference that is occurring, then all the light is reflected. So all these parameters you have to take into account. And what is texturing, what happens in the texturing, as you can see in a texture surface, rather than the being lost, the refracted light can strike other things. So this is how the concept of texturing is. So we have to take care while making film how to do the texturing. And these are the SEM images of the textured multicrystalline silicon surfaces for the solar cell. Then the material thickness and the light trapping, as I have already said you. We can see the light trapping, and also all other things. Now, what are the other reducing recombination losses? These are the other reducing recombination losses. As we can see, this is a recombination versus collection. Okay, what is happening? Photon generates an electron hole pair near the front surface, and the hole recombines at the top surface. And a photon generates as an electron hole pair. As you can see here, the minority carrier is collected when it crosses a junction, and a photon generates an electron hole pair in the base, and then the minority carrier is collected when it crosses a junction, and then a photon generates an electron hole pair near the surface, and then the electron recombines in the base. So this process keeps on happening, and at last what happens, this is electron recombines at the rear. So it starts from here and it ends till here. So recombination and collection in a solar cell is depicted by this process. Then there are current losses. There are current losses, as we can see, due to the recombination. There are voltage losses, as we can see, and then there is surface recombination. Some other parameters that are there are these things: CD resistance, sheet resistance, shunt resistance, and other silicon solar cell parameters. So go through all these stuff, and if you have any confusion, feel free to email me. I'll definitely entertain your doubt. So please go through this website, and in order to show what sir has also taught in the other classes, we can see that yeah, in 30th class it started with the silicon solar cells, and how do we reduce the losses there, and shunt resistance, the concept of shunt resistance, and the types of silicon solar cell, and then what is a silicon solar cell, and why polysilicon is needed, and all this stuff. Okay, surface texturing and all that I was already telling you in short on the websites. And then sir talked about the manufacturing of it. How do we manufacture? It could be a single crystal, it could be a monocrystalline, it could be a polycrystalline, and then the procedure. What is the way? Why is it not environment friendly? And how do we need to replace it? Then sir has talked about the refining of it, then other grades of silicon, then Siemens process for getting it, and in the next class sir has talked about gallium arsenide solar cells, the need of it, and what are the dopants that are used here, and other alternate devices that could be designed in the same domain. Then sir introduced the second generation of solar cells, where he talked about the thin film solar cells primarily on inorganic material, and why they're important to reduce the material cost and reducing the amount. Then inorganic semiconductors and all these things sir talked about. And then sir talked about a silicon solar cell. This is a recap of them. This is a basic structure. If you can see, there is a glass, then there is a SNO2 conducting layer, then there is a textured SNO2, P silicon, then this is I, then this is N silicon, then this is aluminum contact, and the thickness is nearly around 0.5 micrometer. So this is a super straight configuration of a PIN kind of junction. And then sir talked about other possible that structure that are possible from where the light should fall, and deposition methods, different kind of deposition methods are talked about. And then sir talked about the cadmium telluride solar cells, where what technologies are using and how these are important, and what are the structures they are having, and the efficiency comparison, and the device design. You can see the device design here. Here N and P is directly attached, but the P is made a little thicker than N because of this passivation layer is below, and we have to use a low resistive electron layer. Okay, so then why CDS and CDTE is used, how much CDS, how much CDTE should be used, all these things sir talked about. Then the manufacturing of it. And then in the 35th class I talked about the cadmium telluride solar cell processing and all these stuff. Okay, so till now this was there for the week 7 classes, and week 8 class will be shown to you later. So let's wait one more minute, and if see if some other people are joining. If not, then I'll go forward with the class. Okay, so I guess not many people are joining, and I'm also not very well today. So I'll be showing you this. So this is our seventh assignment, and I have made 10 questions based on week 6 and 7 classes. And if you have any doubt, do mail me afterward, because I myself am not very detailed knowledge about the solar cells, but I'll try to entertain it because my seniors are working on it and I have people who can really entertain your doubts. But this assignment is generally made for telling you the answers of the questions that are given to you in the assignment. So let's begin. So the first question is, we can see a typical absorber layer in a CSI solar cell absorbs 43% of the light with wavelength. Have I on my mic or not? Am I audible, Melee and Gaurav?
Yes, sir.
Okay.
Yes,
So a typical absorber layer of a carbon silicon solar cell absorbs 43% of the light with a wavelength of lambda is equals to 1100 nanometer, incident from illumination of 1.5. Assuming that the absorption coefficient for infrared light is, which is alpha at 1100 nanometer, is 10 centimeter inverse, the approximate thickness of the absorber layer in micrometer is, and the options are 426, 693, 562, 503 and 350. And yes, you can try to solve it. I am giving you 4 or 5 minutes. You give a try. Male, you giving a try?
then only the IT equals to I0 into 1 minus exponential of minus alpha t.
Yeah. That's the formula. I mean, give a
This is
try.
the formula.
Yeah.
Yes, yes.
Okay, Mele. Okay, Mele. So I'm showing the answer now because Gaurav is also there. So I mean, we have to take into account.
Yes, yes.
Okay. So yeah. So this is the answer. We can see here I is equals to 43% of I naught, as it is already given in the question, Gaurav, that 43% of the light with a wavelength of this is being absorbed, and illumination is given, and the absorption coefficient is given, and the thickness is asked in micrometer. Okay, so basically we know that I is equals to 43% of I naught is given in the question. Alpha is given as 10 centimeter inverse. We know the formula. It is equals to I naught 1 minus exponential of minus alpha t, where t is the thickness. So it by I naught is equals to 1 minus exponential of minus alpha t. So exponential of minus alpha t will be 1 minus I over I naught. I we know 43. If we consider I naught as 100, that means 43% of the light is being absorbed, which clearly gives the exponential of minus alpha t is equals to 0.57. So minus alpha t will be the ln of the natural log. Remember, the not the log base 10, the natural log of 0.57. So minus alpha t is comes out to be minus 0.5621. So from here we put the value of alpha, then t is equals to 0.5621 over 10, which is 0.0562 centimeter. And we know deci, centi, milli, micro, nano, pico, femto, atto. So from centimeter to micrometer we convert, and we get it as 562 micrometer. Okay.
Yes, sir.
Okay. So do you want to note it down? You can note it down.
Okay, sir. Already.
Okay. Okay, great. So let's move to the second question. The second question is, a solar cell delivers a short circuit current of 7 ampere under 1.5 illumination, and the reverse saturation current is 10 raised to a minus 11 ampere. This is raised to, okay, minus 11 ampere. The open circuit voltage in volt at 300 Kelvin, neglecting any internal resistance in the cell, would be. We have to calculate the VOC when we have been given the Boltzmann constant Kv. We know the value 1.38 into 10 raised to power minus 23 joule per Kelvin, and the electronic charge E is equals to 1.6 into 10 raised to power minus 19 coulomb. We know these two values. So the options are 0.709, 0.640, 0.821, 0.790, and 0.556. So similarly, I'm giving you 5 minutes. You can give a try, and if not, then I'll show you the answer.
Sir, just sir, zoom it, sir, please.
Okay. You're not able to see it now? It's okay.
Okay, 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 sir.
Great.
Okay, sir. Sir, option A.
Okay. Gaurav, Mele, can you tell Gaurav like how did you solve it? Then I'll explain definitely. What formula did you
Sir,
use?
KT by Q ln ISC by I naught plus 1.
Hmm.
Sir, KT by Q is 0.026,
Yeah, that's the direct value. Good.
and ln just calculate that 7 by 10 to the power minus 11 plus 1.
Okay. So Gaurav, I'm showing you the solution. uh, so this is a solution. Okay, so we know the formula as VOC is equals to KT by Q ln ISC over I naught plus 1, as Melis said. KT by Q is we know the direct value is this, ln 7 over 10 to the power minus 11 plus 1. So it comes out like this, where the complete will be like this, and then if you see, it will be around 0.026 cross 27.274, which is 0.709 volt. Okay, why this is one is neglected? If you know, I mean, this is nothing if you compare the whole value of this, so this is being just avoided. Like this is a portion of expansion, but this will not alter the value. So yeah, we avoided it, and then we just put it the value and could find out the ln of this, and just did the calculation, and the answer is this. So yeah, there will be questions like this. Okay, probably the same question can also come, so keep a track of them. Okay, so the next question is this: which of the following are correct for an ideal IV curve? Now you have to explain me, Mele. Gotta take a part into it, because I am myself not very handy in making solar cells. From this is the portion from where it starts, where I am just like you people. Okay, so for an ideal IV curve for a solar photovoltaic device, B is the applied bias, J is the current density, and VOC is the open circuit voltage, and Vmax is the maximum voltage from the device. So which of the following is correct for an ideal IV curve?
Sir, C and D.
Okay, I think I have given the options wrong. The correct option, if you see, are like this. Okay, these are the correct options, and the answers are C and D. So what they have given, dj over dv in who inverse, when V is equals to maximum voltage, it turns out to be infinity, which is not possible. If it turns out to be infinity, how will it work? Dj over dv, V equal to V must equal to 0. No. So why C and D, Mele? What do you think? I mean, could you explain?
Yes, sir.
Yeah, give
Sir,
a try.
in IV curve, sir. Okay.
Hmm. Say, we are listening.
Sir, IV curve, sir, VOC equals to B. Okay, sir. If we take the perpendicular tan of the dv,
Okay.
tan theta equals to dj by dv. Okay.
Yes.
At V equals to VOC,
Hmm.
at V equals to VOC, tan 90.
Hmm.
Tan 90 equals to 1.
Hmm.
Uh, Infinity.
Okay.
And make the inverse, and dg by dv equals minus inverse equals to infinity 1, and when jc equals to maximum, when V equals to 0,
Hmm.
we put the reverse.
Okay. Okay, so for the other viewers who will see it afterward, yeah, Mele has a very good understanding, even better than me, I would say. I would have to think for a minute for tell the answer. So, like we know the IV curve. The IV curve of a solar cell is a superposition, and the equation we can see is equals to I equal to I naught exponential of QV over NKT minus 1 minus IL, where IL is a light generated current. Just to give you a quick recap, if you start it like this without elimination, a solar cell has the same electrical characteristics, just like a diode. But when the light is shining, you can see the IV curve shifts as the cell begins to generate some power while illumination. And if you further illuminate it, the intensity will be shifted to a more extent. So this is how. And the solar cell curve, we usually represent the flipped version of it. So this is basically a IV curve standard plot, and this is the maximum current and maximum voltage. This is VOC and this is ISC, which we have already explained. Now using these parameter, we have to see the question. The question is saying that which could be the right for VOC. Okay, so as Melis said, this will be the 10 of this equation. If we take the 10 theta of that, then this comes out to be infinity, and this comes out to be 0. But in these options, they were written reversible. you can even remember it. When v is equals to 0, then only dj over dv can be infinity, and when v equal to voc, then only dj over dv equal to 0. These two parameters are not possible. Okay, so this is a very straightforward question that you can remember. Okay, so let's move to the next question. Question number 4. It is the method adopted to reduce the surface recombination in silicon solar cells. The options are use of anti-reflection coating, surface passivation, textured front surface of the solar cell, and heavily doped rear surface of the cell. I just talked about it when I was giving the introduction. Give a try.
Sir, surface passivation.
Okay, surface passivation will reduce the surface recombination. Why?
And sir, one thing, heavily doped rear the surface of the cell.
Okay. Why not a texture surface and the use of anti-reflection coating? The
Sir,
anti
the textured surface naturally give the upper texture for reflection purpose, sir.
Okay.
Texturing is done
Okay. And why
for
not?
absorption all the lights, and
Yeah.
by changing the top layer to 111 to 000.
I get it, but if we are doing the texturing, if we are maintaining it, then will it not affect recombination at all? You're right, Malay. Don't be confused. I'm trying to confuse you. Absolutely not.
Yes,
It
yes,
has no process. And the first option is anti-reflection coating. That is just dealing with. That is just related to the light coming to the surface and getting reflected. Now, when this
yes,
charge carrier starts happening, this electron and hole pair starts forming, and then this whole process continues, and at last it recombine. So at that, in these things, which parameters actually play the role? These are all are of our concerns. So if I show you if, the thing that I was talking to you, where was it? Mm. Yeah, this was related to the surface texturing, how this texturing plays role, and the optical losses that we already talked about. One more thing was there that I was talking to you. Where has it gone? Reflection coating. Uh, yeah, there it is. Recombination losses. Yeah. So this was the recombination losses. See, when it only starts happening when there this electron and hole starts forming. Now when a photon is generated, it keeps on passing and passing by the minority carriers. Now it start from here, then again this light will shine here, this will go here, this will go here, this will go here. So only from here we can be sure that there are only two things which are responsible for it. So the correct answer to the question is, as I can show you, B and D, the surface passivation
yes,
and the heavily doped rear surface of the cell. Okay,
yes, sir.
so now let's move to the next question. The next question is, Stabler-Wronski effect is hydrogenated amorphous silicon solar cell lead to the increase in shunt resistance, defect density, or decrease in the power output, increase in the power output with light soaking time, or decrease in the density of tail states.
Sir, oh, uh, decrease in the power output with light soaking time. First, this one.
First of all, you tell me what is Stabler-Wronski effect.
Stepler-Roxy effect is, sir, in amorphous silicon solar cell
Hmm.
due to the dangling bonds.
Hmm.
Due to the dangling bond effect, when there is a light shining on it, sir.
Hmm.
Okay, this light soaking power output is decreasing in graph,
Okay.
so that it will decrease very drastically, sir.
Hmm.
This is the Stepler-Roxy effect.
Yeah,
They will
you're.
recombine. Actually, main case is that, sir,
Hmm.
there is a blank blank gap, blank gap in the molecule.
Hmm.
So, and this blank gap, the ions are going there and recombine
So is there a way we can reduce it?
near surface. Yes, near surface there is a blank bond, a blank. atom, I think, like trap
Yeah, yeah.
in
So
material.
what is the way of reducing it?
So by you group with the hydrogen or the bond with the hydrogen atom in
Okay.
that hydrogen passivation.
Even we can use more thinner layer of amorphous silicon together with another material which gives the concept of multi-junction solar cells. If you are
Mighty jump.
yeah, and we can even
Yes,
use the
absolutely.
microcrystalline silicon instead of amorphous silicon. Okay, so for the viewers later, the answer as he said is right. The answer to the fifth question is B and C. Okay,
Yes.
so increase in the defect density and decrease in the power output with light soaking time. So let me explain what is Stabler-Wronski effect. See, in verse if I say that in common lay language, the Stabler-Wronski effect, it refers to the light-induced metastable change. So it is the property. It is a property of hydrogenated amorphous silicon. So what happens? When there is a defect density of hydrogenated amorphous silicon, which is termed as ASIH, it increases with the light exposure. The more will be exposure of the light, the defect density will increase, which causes an increase in the recombination current. Now when there is an increase in the recombination current, it reduces the efficiency of the conversion of sunlight into electricity. So the Stabler-Wronski effect is the property of hydrogenated amorphous silicon, and due to the result of this, it affects the efficiency of the conversion of sunlight into electricity. And in order to reduce it, as Mele say, we can do the same thing, and except that what we can do, we can either use a nanocrystalline silicon instead of amorphous silicon, or we can operate at a little more higher temperature, which can be there is a new method called photovoltaic thermal hybrid solar collector. There we can do it, or we can stack one or more thinner layers of amorphous silicon together so that it forms a multi-junction solar cell, so that a dangling thing does not occur, and the higher electric field is there which applies in the thinner layers, which appears to reduce the SWE. So the options are to increase in the defect density and decrease in the power output with light soaking time. Okay. The next question is, which of the following are the correct sequence of manufacturing of single crystal silicon? So firstly we find out the grade, or we find out the semiconductor, and then what we do the metallurgical grade, or we directly go for the single crystal silicon. What are the correct order? So have a look and try.
Said option C.
Okay, so metallurgical grade silicon and then purification. It is a direct question from the figure given by sir, right? In a class.
Said
Yeah. So option C. So for the viewers who are viewing, this is right, and this question is directly from a class. In one of the slides you can see like this a graph that has given where these all the steps are given. So the correct options is option C. Okay, so let's go to the next question now. The next question is silicon nitride coating on the emitter in polycrystalline silicon solar cell. It leads to reduce in carrier recombination, absorb light, reduce reflection loss, reduce surface recombination, reduce the defect density. I am giving you 2 minutes. Think and then tell.
reduce the reflection loss.
Okay, and how will you reduce the reflection loss? Acha, where do we coat it? Do you have any idea?
Just below the just before the contact coated this upper layer is chemically is
Okay, so we can simply say now, Mele, it is an anti-reflection coating. So what happens? A silicon nitride layer is just is used to reduce a cell's front surface reflection, and it also is beneficial in order to minimize the recombination at the silicon surface, where there is a silicon surface. So we generally it uses the concept of constructive interference to reduce the reflection, which I was showing in the video only. And what
Sir,
happens?
can you repeat what is the construction?
Yeah,
What process?
the reflection. Just a minute. The constructive interference, I'm saying, instead of reflection, the
Constructive
constructive interference happens. And then this hydrogen content is also deposited, which is really very beneficial for the multicrystalline wafers. So let's show the answer to the seventh question is definitely the option number C. It reduces the reflection losses. Let's move to the next question number 8. The question number 8 is saying the intermixing of CDS, CDT and CDTE solar cell leads to. Read the options and tell the correct answer.
option D.
Why?
Because when the intermixing means in the layers, when CDS and CDT mix together.
Hmm.
So sir, it mix together, the CDS have the higher band gap,
Hmm.
and CDS and CDT is 2.4 and 1.4, I think.
Hmm.
It will make higher band gap. So in higher band gap, sir, lower wavelength are not absorbed.
Great. Good.
So that's why, sir, the quantum efficiency of lower wavelengths decrease.
Okay. And except that even though the question, the concept you said is right, but even after that, instead of all these things, you're using this CDS CDT mixing, you have to take care of the way you are the way of deposition.
Deposition,
Yeah, the way you are
CDS
manufacturing,
deposition.
everything matters. It does not matter. And the contact and the material plays a significant role. Okay. So, and yeah, but slowly we are going to the perovskites now. Let's see what happens. So the answer to the question number 8 is D. What happens? The intermixing of of CDS and CDT layer in the CDT source will lead to a decrease in the quantum efficiency at lower wavelengths, and this is based on the band gap concept, as Mele already said, which is already explained in the class. And you can see my previous class recording, where I have explained which is the right material and what is the band gap domain, which is really necessary in order to design a solar cell. Okay, so let's move to the next question. The next question is question number 9. Which of the following materials cannot be used as solar cell materials? The options are silicon, gallium arsenide, cadmium sulfide, or lead sulfide. Same concept, same question.
So lead sulfide.
Okay, others are also
Lead
there.
sulfide.
Others are also there. Let me ask them also. Gaurav, can you explain this answer? Can you tell what is the answer? What why lead sulfide? Gaurav, are you there?
Yes, sir.
Yeah. So as I've shown you the question, uh, which of the following materials cannot be used as solar cell material? Silicon, GAS, CDS, and PBS. We know the answer, but why PBS? Do you know? Okay, no problem. I am explaining it. As he said, the concept of band gap. So what happens, Gaurav? Obviously, these three solar cells we have already read. I have already written it in the PDF that I'll be providing. You have a look over it afterwards. So what happens if we are using the PBS as a source cell material now? Then most of the solar radiation will be absorbed only on the top layer, because this PBS, this band gap line, is not in accordance with the silicon gallium arsenide or CDS, or the band gap domain which is required for making a solar cell, which is generally 1 to 1.5 electron volt. So it will absorb on the top layer of the solar cell, and it will not reach to the depletion zone. And if it will not reach to the depletion zone, then there will be no formation of electron and hole pairs. Then Obviously, this material cannot be used as a solar cell material. Okay, let's move to the last question of today. So the cells are connected in series in order to increase the voltage rating, increase the current rating, increase the life of the cells, or none of the above.
Voltage rating.
Why voltage? Why not current? Melee, why not current?
In series,
Hmm.
current is constant, na, sir?
Great. Simple.
Voltage is varying.
In,
Yes.
in series, the current remains a constant, and if we are
Yes,
connecting the
sir.
cells in series, that means we need a higher voltage from it. So, to increase the voltage rating, the cells are connected in series. So the answer is obviously the option number A, increase the voltage rating. So that's all for today, I guess. Then there will be a last assignment next week, and if you have any doubts, feel free to email me. If you have any question, Mele, feel free to email me afterward. Okay.
Sir,
Sir,
hello.
Yeah.
Sir, I want your email ID, sir.
What?
Sir, I don't have your email ID.
Okay, you don't have my email ID. I'm writing it again. Are you not following the drive link that been provided where we are uploading our assignment solutions and the recording of the videos of the this TAship session? Gaurav, this is my
Sorry,
email.
I can understand, sir.
I'm just saying, are you not being provided with a link where we are uploading the YouTube videos and the assignment solution in the PDF form and also the classes recording of the classes every single week? Like there are three TAs, all the three TAs take the three classes and then we record it. We upload our presentation, we upload the solution of the assignment, and we also upload the recording. And we have a YouTube channel also separately where you can watch it. My YouTube channel.
Which YouTube channel?
Okay, let me show you.
sir, already is given in the
It's given in the assignment. I think he was not following.
assignment.
Yeah,
Given in the assignment, sir.
yeah. I have been giving, and
Section, lecture section.
yeah, and Malay, Malay. I'm saying Gaurav.
Yes.
Gaurav, let me show you this. This is a drive where I'm just sharing the link also. Video. So this is a PM RF solar photovoltaics spreadsheet where we are constantly uploading the YouTube link, the backup video link, the presentations, and the solution to the PDF. Everything we are constantly uploading. You can see from here.
Okay, sir.
Yeah. So I'm just giving you this link also so that you can access it.
Sir, you also have PMRF, sir.
Yeah.
Sir?
Tell me what you want to know about it.
No, just asking.
Yes, I am a PMRF Malay.
Yes, sir,
I
yes.
am a
Yes, sir.
second year PhD student in material chemistry and the Professor Sain Bhattacharya in Advanced Functional Material Lab in Aiza, Kolkata. Okay,
Oh, sir, where, sir? I am Kolkata.
Either IISER Kolkata.
Oh, I yes. Okay.
Yeah, and I work on perovskite. If you want to uh, see some paper that I have published, it's my second year only going on. So
Okay.
yeah, I have two papers which are being communicated, and two are being published. Both are co-authors, but let me show you just for the sake of increasing your interest. Yeah,
Yes.
and I recently started my. You can see I work on perovskites mainly. So these are the articles that I published. Spacious twist two-dimensional tin bromide perovskite leading to the immense stable near unity photoluminescence quantum yield, and where we have talked about a PLQI of different material in 2D tin bromide perovskites. And this is another paper of me where we have used a layered material in order lead free material. We have made it water stable, and then we have tried to you can say use it for some biological purpose, DNA degradation and guanine oxidation. These are the two articles which have already been published. So yes, if you have any doubt regarding PMRF, how to, like, if you're planning, you can even talk to me afterward. Email me, I can give you my contact number. You can talk to me if you're planning something. Okay. Okay then, Male and Gaurav, if you have any
Yes,
doubt, feel free to email. I'll definitely try to entertain it. So I think that's today for the class. Let's wrap it up. Okay.
sir.
Yeah.
Sir, next Saturday you take the class.
Yeah, I'll take the class next Saturday for last class.
Okay.
Okay. Okay.
Okay, sir.
Okay. See you.
Sir, I think last is the final class
Yeah. Last
because
will.
after
Yeah. That will be the final class, and after that you will be having exam. Yeah. Okay.
sir,
Yeah.
just give me some ideas about the final exams. The
Okay.
question patterns.
I today I was thinking that today only I am going to have the meeting with all the two different Ts, Ravi and Hari Shankar.
Oh,
And
oh,
Hari Shankar is in IIT Kanpur. Like his co-PI is, I think, Professor Ashish Garg. His co-PI is Ashish
okay,
Garg.
okay.
So he will have a direct chat, I mean communication with sir, and then one of us will definitely tell you the actual like idea of how the question will come. Everything your doubt will be cleared before that. By this week, I'll one of us
Actually,
will definitely clear it.
last lecture, Harisankar sir showed me a video, sir,
Hmm.
at IIT Kanpur,
Hmm.
how to make a parasite cell coating,
Hmm.
just one cell.
Hmm. Hmm.
Just he will show me a video on
Hmm.
IIT Kanpur.
Hmm. Okay, no, yeah, I remember. I also showed you one video, no? A
Yes, sir, yes,
very small video, if you remember, uh, solar cell related. I don't know if I'm having. I have shown you, right?
yes.
Okay, no problem. If there is something like this, I can show you. In the next slide, I'll try to show you the full procedure.
Okay, sir.
Okay, then feel free to email, and then okay, okay then. Bye.
Okay, sir. Thank you.